I'm pretty good. I
Do you
just
mind it? Sorry, go ahead, go ahead,
go
go ahead.
ahead. I was just gonna say I just wrapped up my everything for the semester, so
Mm.
I'm just you
Great,
know taking it
congratulations,
easy. Yeah,
congratulations.
thanks.
What year are you, by chance?
Third. This is my third year that just wrapped
Hmm.
up. Yeah.
Yeah, nice. Do you mind if this is recorded? I just want to like have something to show to my
Yeah,
friends.
that's
Okay,
fine. Yeah.
great. All right, yeah, I like to keep this just relatively short. Just we have just a couple questions that was interested in your experience and wanted to ask you about. So, it's Dr. Maesumi. Am I saying that right?
Um, Not doctor yet.
Not yet.
Soon maybe, eventually.
Of
But
course.
yeah. Um, you
Uh,
can just call me Arman though. Yeah,
Arman?
that's fine.
Okay.
Yeah.
Nice to
Mhm.
meet you. I'm Mihir.
Nice to meet you too.
So yeah, it's great to see you and speak to you. So yeah, could you tell me a little bit about yourself and your journey in computer science?
Yeah. So I grew up in Texas, Southeast Texas actually, near Houston. Um, I got into CS related things quite young, maybe around like 11 or 12 years old. I was like toying around with basic programming stuff. And actually, back then was when like YouTube tutorials started to become
Mm.
quite popular. That was like the dawn of the
Hmm.
programming tutorial on the internet. So that's basically how I learned back then. Um, Throughout high school, things got more advanced. I kept pursuing it. And then I eventually went to UT Austin for my undergrad, did computer science, and got involved in research. So I guess we'll maybe talk about that in a bit. And then immediately after undergrad, I went to Brown for my PhD. And yeah, so now I'm working on essentially the intersection of deep learning and computer graphics. So things like um, if you watch like a Pixar movie, they
Sure.
have tons of like 3D models and like the models are textured and these things. So I deal with um, the creation, manipulation, and analysis of the assets in computer graphics. So like I guess maybe people know about things like Dolly 2, like generating
Hmm.
images
Of
from
course.
text. Something that I would be interested in is generating a 3D object from text
Mm-hmm.
or texturing those objects or things like that. Um, yeah, so I guess that's my like high level background.
Hmm. Yeah, no,
Yeah.
that's very interesting. I can definitely see like a future for like yeah, the videos, creating a video from a single sentence and like just like a
Mhm.
paragraph description of video and creating it. Yeah, I think that's really interesting. So I know you mentioned YouTube tutorials and all these different things as your little introduction into like computer science in general. Was there a particular moment that specifically drew you towards so I know on your website it talks a lot about your interest in 3D art. Was there
Mhm.
any like specific moment that drew you towards your more specific path, like you said, deep learning and computer graphics?
Yeah, so I guess there were a lot of fortunate things. So a lot of people, aren't sure what they want to do until later in life, which is totally fine. But I was fortunate to just sort of have like multiple interests that all coalesced.
Hmm.
So in like middle school, high school ish, I started toying around with 3D rendering, like, just making like cool little artistic scenes, rendering them, 3D art, that sort of stuff. And that interest was sort of separate from my like computer graphics or my computer science interests at the time. Um, like one was more artistic and one was just like, you know, as we know, computer science. And then in undergrad, those interests sort of merged a little bit. Like, um, there are like computer graphics courses in CS departments, and there you learn about the science of computer graphics, so like the mathematics, the algorithms that are used to say like render a 3D scene, or to define geometry and these things. And it's a super deep and also broad field. It's one of the broadest fields in computer science. Um, Computer graphics touches on so many things. And during that time, like when I was graduating from high school and getting into undergrad, that's when deep learning started to really kick up. That was around 2017. Like that's when things went sort of like exponential
Mhm.
in terms of popularity. Um, so I like just by good fortune, I guess, like good timing, uh, that's sort of when I entered the bubble.
Mhm.
And yeah, like everything was just natural at that point. It was like, oh, these are all really interesting topics, and I've been interested in these things for a while. So yeah, I just pursued it. Yeah.
Yeah, of course. I saw your I thought the 3D the chess piece rendering of it like
Hmm.
that recursive I thought that was really really cool. And I know how you were saying how you think how those are like separate passions like your 3D art or like when you started at least there were separate
Hmm.
passions of 3D art and you know AI deep learning all these different things. So do you see like any of your creative processes from thinking about art play over into how you think about deep learning, AI, and all these
Hmm.
different things? Yeah.
Yeah, that's a good question. So, well, I would say there are a few axes to this. So, of course, like one very important part of doing a PhD, one of the most important things I'd say is learning how to communicate what you're doing. Um, so, like the most typical thing that any PhD student is doing is writing papers, right? So they have to, write a detailed document explaining everything that they did, what motivated it, this and that. And the presentation of that is super important. And part of that presentation is visualizing what you do. So definitely the 3D art stuff has informed how I've presented work, but also in terms of just thinking about the problems and like visualizing what's going on. So in deep learning, things get really difficult to like even visualize very quickly because you're sort of dealing with things that are not easily interpretable. Like a black box is
Black
like the
box.
sort
Yeah.
of
Yeah.
thing that people say exactly. And not just that, but you're typically operating in a space that is way higher dimensional than what we're used to. So things, it's very difficult to interpret in that way. But at least um, being able to have a mental grasp or image of the most basic version of your problem and like sort of being able to close your eyes and like mess around with it in your head is very important. Um, so yeah, in some like vague respect, I would say these things inform each other. But
Sure.
yeah.
Yeah, I think it's probably challenging to draw the similarities between the two. One is a very abstract process, and I guess
Mhm.
deep learning is also sort of abstract, but like you said, it's hard for us to visualize those things. So, I
Mhm.
really connect with that idea of really having a fundamental understanding of your basic thing that
Mhm.
you're trying to work on,
Yeah.
right? So, would you be able to give us? So I did. I saw the recent paper you guys published in SIGGRAPH, and
Mhm.
it was on the unified models of noise patterns.
Mhm.
Uh, could you give us like a simplified overview of what that research was on?
Yeah. Do you want me to share my screen or would you rather a
Um,
verbal? Um,
if you want to share your screen, go for it. I think.
okay.
Do you have that
Well, let me check.
access?
Hold 1 second. Yeah, because the nice thing about graphics is that, oh yeah, I do have permission. The nice thing about graphics is that everything is a visual
Mhm.
sort of thing, right? So it actually is much easier to explain with a visual aid. Um, is everything visible?
I think I am having a little bit of like it's like kind of
Oh,
buffering on my end, but I think
I see.
Uh,
You can let me know if it doesn't work, I can just do a verbal explanation, but
there it is. It just popped up. Yep.
okay.
Mhm.
If I start lagging, let me know.
Sure.
Sometimes my internet is like a little
Hmm.
bit annoying. So yeah, the high level topic here is so in computer graphics, um, let's say we want to model like a table in a Pixar scene, right? And that table, maybe it's made out of wood, so you expect it to look like wood, right? So it has to have these like interesting like sort of undulations and coloring and whatnot. So uh, the way that computer graphics people model randomness in these sorts of objects is through something called procedural noise.
Hmm.
So noise in the mathematical terminology, noise can be thought of as like white noise, like static on a TV.
Yeah.
So static on a TV is like pure noise. It's like completely noise. Um, but in real life, when you look at like a brick or a tree or a shoreline, the randomness that you see is more organic and like smoother, but it is random. So in computer graphics, we have something called procedural noise, which is meant to model those like organic random things.
Hmm.
Um, so on the screen, like you can see like our teaser figure for the paper, which is the SIGGRAPH logo written with these like different types of noise.
Noise.
And so
Yeah.
what we're tackling is in graphics, you can think that we have like this huge library of different types of noise, but they don't really talk to each other. Like they're all their own uh, essentially you can think of them as their own function written in like C++ plus plus or something.
Hmm.
Uh, well, what would be nice is if you could say, oh, I want to blend between noise one and noise two organically. So that becomes a pretty ill-defined problem because
Hmm.
you don't really know what is a smooth blend between two random signals.
Yeah.
So if I go down, this is like one of the interesting figures in the paper. So this is like a blend between two different types of noise. It
Mm.
looks like, zebra patterns and like
Yeah.
hay or something. And like the action in between is like it looks organic. It looks like things are sort of like melting into each other.
Hmm.
Um, so we trained like this diffusion model. Uh, I'm not sure if there's like familiarity with
Yeah.
the
Yeah.
group,
Of
but
course. Hmm.
okay. So yeah, we trained a diffusion model essentially on like uh, many different types of these noise functions, and the data set that we had. So the one of the key contributions of the paper is that we had a data set where all of the images were only one noise type, like a
Hmm.
fixed thing. Uh, and we sort of came up with a way for the diffusion model to learn how to blend between them, even when there's no data for that
Hmm.
sort of task. So here are some more images. Um,
Yeah,
so
it's
yeah,
really
this.
interesting.
Mhm,
I see you were talking about like organic. I'm getting like images of like a tree, like a kind of like
mhm.
the like
Yeah,
a burnt
the
a burnt
age.
kind of tree. Yeah, an
Oh,
aged
sure.
tree. Yeah, yeah, an
Hmm.
aged. That's sorry,
Yeah.
that's what I meant.
Hmm.
Like the rings, everything. Yeah, it's very fascinating.
Yeah. Yeah. So, um, yeah, in computer graphics, like if I go on Google here, if I search material graph, uh, wonder. So, a 3D artist making like a wood texture or, cement texture or something like this, what they would see is like some UI that looks like this, where they have these nodes that are connected. And this is a what's called a computation graph.
Hmm.
So you can imagine you're trying to define different properties of the texture through like a procedural or like algorithmic way, although it's presented in like this visually pleasing interface.
Sure, and all those
So
would be like
mhm.
different rules for how the texture would be, sort of.
Yeah, yeah. So like typically how it works is you would have some nodes. So each of these boxes is one node,
Hmm.
and uh, maybe you have a node that produces like one of these images. You feed that through some transformations that give it color and like distorted this and that, and eventually you end up with wood or whatever texture you want at the end. So this is like fitting into that big uh, artistic sort of interface, I guess.
Hmm.
Yeah.
Yeah. It's a very interesting tool to be able to blend the different types of noises together. Um,
Mhm.
yeah, I think that's very interesting. It seems like a very complex topic. So what would be some of the like key challenges that you faced during that process?
Yeah. So I guess I'll stop sharing my screen here just in case it's lagging.
Mhm.
Um, okay. There were actually this project took over a year to
Wow.
finish,
Mhm.
from beginning to end. Um, we started with a slightly different goal, which was challenging. Um, Perhaps uh, the most challenging bit, I think, um, is so we have this model, and like I said, we're training it with a data set that does not actually support the output that we want. So the
Mhm.
data set does not have any blended images, but we want blended images. So the question was, how do we impose the right structure on
Mhm.
the neural network to produce what we want? And finding the right set of um, you know constraints was the biggest challenge.
Mhm.
Um, I guess it becomes a bit technical. I could get into like the absolute most technical bit if that's like
Uh,
useful. But yeah, it's up to
no, I think that
up. Mhm.
that is that does seem very complex. Like how would you go about training the model without having like what the goal output is? How do you like validate whether or not it's producing
Mhm.
something that's what you're looking for, right? That's
Right. So okay, in our case, actually, the validation was that's still unsolved.
oh.
So like, if you wanted the computer itself to recognize, oh, this is good and this is bad, that's actually its own problem,
Hmm.
which maybe we might solve it in the future or someone else might solve it. We were sort of using our own eyes to say, oh,
Sure.
this
Looks
model is producing
natural.
something good, this one's not. But in terms of how do we formulate the training process so that these things do look good?
Hmm.
Yeah, so the technical bits there. Um, so actually, I can go back to the
Sure.
page. Um, so okay, there are two problems, and I actually with this page, this project page, I tried to write it in the most like simplified and accessible way because
Hmm.
at the end of the day, the insights are actually quite simple to write down, uh, as long as you have some like background knowledge.
Sure. Hmm.
Um, so uh, diffusion models use UNet architectures. So a UNet is like a neural network that has this sort of like bottleneck in the middle. So it
Yep.
compresses the signal spatially into something that's like, you know, a fraction of the input, and then
And
it blows
scales
it
it
back
back
up.
up.
Yep,
Yeah. Yeah.
exactly. So, okay, UNets are nice. They have like some nice properties and they're good for diffusion models. So if we accept that, okay, we're using a UNet, then something that we have to recognize is that when we tell the UNet, okay, in this area I want this type of noise, and in this other area I want some other type of noise, what it's going to do is sort of smear uh, that constraint that I'm telling it. This is it's a bit hard to explain why it does this, but since it's compressing things downward, uh,
Hmm.
that sort of so if you look at this block here,
Yeah.
imagine this is like the canvas, and these colors are saying, okay, I want different types of noise on these different colors. if you compress this downward, then these colors are sort of gonna blend into each other, like sort of like uh, average out,
Yeah.
and then your output ends up looking like an averaged out image. Like it would be like
Yeah.
if we just averaged out a bunch of different types of noise, and it would
So you
look
wouldn't
ugly.
so you wouldn't have the distinct types of noise. You just have just some mix of everything together, whereas you're looking for a blended variation of specific different noise types.
Right. Yeah. We want someone to be able to like direct the
Hmm.
model or like art direct it. Say like, okay, in this area, I want this type of noise, rather than the whole thing getting
Hmm.
averaged out. Okay, so that's like a fundamental limitation of the UNet. Like it's
Hmm.
sort of just it's doing that by its own nature. So we came up with a way to uh, force the model to obey this sort of conditioning. Uh, well, actually, maybe I should mention the second problem, but this is a little bit more technical. So uh, with diffusion models, uh, so a diffusion model takes in a big block of noise and then slowly denoises it
Yeah.
um, towards an image.
Hmm.
So, okay, if you think about if you put your mind in the image space, so imagine you're in a space, not a three-dimensional space, but a very, very high dimensional space
Sure.
where any point in that space is an image.
Hmm.
Okay. So we start with our noise image, which is some point in that space.
Hmm.
Okay. And then each diffusion step, like the
It's
denoising
closer.
step, yeah, it pushes the point closer to
Hmm.
whatever image you want.
Sure.
Now, the problem is, um, you can imagine if we're trying to denoise the noise to look like this left image. Okay, that's like one trajectory through the space. Like
Hmm.
you can imagine the whole path, you could trace it out. But now if we want, if I said, okay, the left side of the image should look like this, and the right side should look like some other noise,
Hmm.
then you're sort of forcing the network to kind of go down two paths
Hmm.
simultaneously. But as I mentioned, the training data doesn't have any multi-noise samples, so it never sees such a thing. So it can't really handle this like multi-trajectory denoising. So these are like two problems that we assessed, and the way that we did this is is actually very simple. We take like one of our data set samples, this image, this is like some type of noise,
Sure.
and then we take uh, random other noise types from the data set and cut them uh, in random ways. So here I'm
Mhm.
like cutting rectangular
Yeah.
patches,
Hmm.
and then we just paste them onto each other.
Okay.
So you get this like collage of noise.
Yeah.
And like this is not something that anyone would want to use in
Hmm.
like their texture or whatever.
Yeah.
But the purpose here is to alleviate those previous two issues. So now during training, the UNet needs to uh it can no longer like blur the signal like I said before. Like if it
Hmm.
averaged things out, then the training loss would be bad.
Yeah.
Like so it's forced to like respect this sort of these like hard boundaries
Hmm.
and these like localized features. Um and this is like giving it a natural way to like denoise multiple trajectories. So
Hmm.
here it would have to denoise five different types of noise simultaneously.
Hmm.
Um, and by the way, one annoying thing is that, okay, I refer to this as noise, and I
Hmm.
also refer to like diffusion noise as noise. These are like different, totally different things.
Of
So
course.
when I'm saying like denoising, uh, there's like a overload in terminology, but like
Hmm. No, do
graphics
you,
noise is different than like
yeah, the
diffusion
input,
noise. Yeah.
yeah, and the output of what you're trying to receive from the unit. Hmm.
Yeah, yeah, exactly.
Yeah.
Um, yeah, so that's like the contribution, and there are some other aspects of the work that um, okay, maybe those would be too deep in the rabbit hole, but I would be happy to talk about them. But yeah,
No, for sure.
yeah.
Yeah, no, it's actually it's very fascinating how your method uh forced the model to have to, like you said, respect the different noises. But I thought that was interesting that the loss would be so low that it couldn't just take the average, because I would think that, even if the loss was low, that would be the its most efficient way. But clearly
Mm.
that's not what happened. But yeah, that's a very interesting solution to those two separate problems. Mhm.
Yeah, yeah.
Yeah.
I guess so. With these types of projects, um, it's always nice to have hindsight to analyze not just your solution, but what was originally wrong with what was missing,
Mhm.
and like assessing those things after the fact. So certainly some of these um, insights came later, like possibly even we uh, after we had something that was working. You know,
Mhm.
like you try things um, sometimes through a gut feeling, or maybe you
Yeah.
have some like evidence, and then you try to think about, okay, why did this work? That is actually something that's quite common in deep learning,
Mhm.
to do this like retrospective analysis, or like sort of giving a justification for something after you demonstrated it. Um, so yeah, in some sense, you definitely could arrive at this solution through like, a principled approach, but sometimes, just experimenting, even with like a simple solution is like, it can be
Yeah.
fruitful. Yeah.
Mhm. For sure. Lots of technical. I thought it was really interesting that big deep dive into your project. I thought that was really interesting. So just two more like surface. I guess the first question is kind of deep, but two more questions just to wrap it up here. So uh, on that research paper, you had people from Adobe, and I read on your website you were also working at Adobe for a little bit of time.
Mhm.
So coming from both academia as a PhD student and also learning, being part of the industry, what are some key similarities or differences you've noticed in terms of like the research approaches, the goals, and the challenges from these two separate fields? I know sharp deviation
Mhm.
from what we were initially talking about, but yeah, lots of yeah.
No, that's a fantastic question. Yeah, I mean, uh, anytime I meet someone that's asking me about PhD stuff, they ask me, okay, are you trying to work in the industry, or are you trying to become a professor?
Mhm.
So I'm also thinking about these differences myself. So it's definitely good to think about that early. Um, yeah, so I did work at Adobe Research two times now. One was remote, and one was this last one was in person. Um, yeah, so certainly the environment is a bit different, because when you're doing a PhD, your PhD advisor, the professor that you work with, is, they have lots of things going on, uh, teaching lots of other students, university, um, things that they have to do for the university.
Mhm.
Um, so you don't typically have a lot of face-to-face time with your advisor to like sit down and say, oh, what did we do yesterday? Or,
Mhm.
what's the update today? Rather, it's usually like a weekly thing, or sometimes some people meet with their advisor once a month. So the feedback that you get is much um, less frequent. Whereas, when you're working at these companies, you're in the same space. Uh, you're having lunch together pretty often, and like you can just go whiteboard a problem with
Mhm.
someone, like, randomly. So that
Mhm.
was an interesting difference. Um, it definitely it does force you to like communicate what you're doing more frequently
Yeah.
to your collaborators, which is a good thing, I think. Um, yeah, so that like in terms of the work environment, that's like a big difference. In terms of the problems that you work on, that can also be very different depending on where you work
Hmm.
and like what lab you're working in. So, some companies don't want to sponsor like certain types of projects,
Hmm.
like more theoretical or, projects that don't have a clear application to
Application,
like
yeah.
some
Product or
product exactly. Um, Adobe Research, they're not very strict about things. Like I was working on, so this noise project that I just talked about, that could be implemented in some Adobe product,
hmm
although it wasn't like something that we explicitly talked about. Whereas my second Adobe internship, that one, like it was like more theoretical,
hmm
or maybe not theoretical, but more forward looking rather than like an immediate, you know,
Sure.
product. And then in academia, like, I mean, you can basically work on whatever you want up to, the satisfaction of your advisor. Like,
Advisor.
so there, people typically work on more, less applied work, on average. Um, yeah. So, and then I guess the final thing that I'll say is that, when you're working at these companies, you get to meet so many people that, other PhD students, other researchers, people from other companies. Um, so that's like super useful. I'm not the type of person to explicitly network or like go networking. I'm not too fond of the explicit activity of doing
Yeah.
that, but like it is super useful to know people. Like that is probably the most uh in terms of contributing to your success, apart from like your own work, knowing people is probably the most important thing.
hmm
That will get you, accepted into either universities or uh, jobs or,
hmm
getting funding or anything in between.
hmm
So yeah, it's very important to, you know, get to know everyone basically.
Yeah, for sure.
Mhm.
And then one last question to wrap it all up. You touched on knowing people in terms of academia and industry. So just last question. Um, what advice would you give for high school students like us? You've
Mhm.
gone through this process yourself. What advice would you give for us who are interested in careers in AI and 3D
Mhm.
computer vision and graphics?
Mhm. Yeah, I would say the single most important thing from my perspective is having like some uh, I don't want to say drive, but just being inquisitive and having initiative. I think
Mhm.
initiative is the right word. So um, don't wait for, someone to tell you to start learning XYZ.
Mhm.
It's if someone is from, a very early age, just, having their own initiative to start projects, to learn things, to get their hands on like, whatever they are interested in, that is like the probably the most important thing. Um, and then once you get to the point where you can reach out to someone and say, "Oh, this what you're working on is interesting. I'd like to be a part of the research." Uh, Having those things and being able to present them like, "Oh, I already know these things. I know how to
Mhm.
do this." You can look at my GitHub and see that I did XYZ.
Mhm.
That is like a very useful reference apart from, getting good grades and everything. Like what these professors would look for, like once you get into undergrad and you want to do research, your job is then to convince professors that you can do research.
Mhm.
It depends on which university you are at. You know, some smaller universities, it's a little bit easier to have a, personal relationship with professors. If you're at a massive university, then you need to um, stick out a little bit somehow.
Mhm.
Um, but yeah, what they're looking for is someone that already knows a little bit. If very little about their topic, then it's hard for them to instruct you in a research capacity. So yeah, having the initiative to just work on things, uh, I would say doing is the best way to learn.
Mhm.
If you want to, oh, this generative model thing looks interesting. Don't just read about it, but actually try to do the most basic version of it, get
Yeah,
a baby result, and then try to see where you can take that. That is the most important thing. Um, yeah, I would say
sure.
just having the
Initiative.
initiative. Yeah. Hmm.
Initiative, right.
Yeah.
Well, thank you so much. We really appreciate all the advice you've given us and all the insight. I love learning about your
Hmm.
project and um yeah, your advice was fantastic. So I really appreciate all your time, Arman,
Hmm.
and thank you.
Yeah. Thank you very much. This is a good sign of initiative for you and your group. I didn't have an AI group
Uh-huh.
or even a CS group in my high school, so like definitely you're doing a fantastic job with this. Um, and yeah, like next year for you, if your group wants to chat with me personally or something,
Of
like I would,
course.
you feel free to reach out and
Sure.
yeah, that would be great. Yeah.
Of course. I really appreciate your time. Thank you so much.
All right. Thank
Uh,
you.
Have a
Have a
nice
good
day.
one.